Okay, so good afternoon. Welcome to the talk of Dr. Andreas Schneemann. Uh, okay. Welcome, Andreas. It's a pleasure to have you here for the talk. And before going into the talk of Dr. Andreas, so Andreas did his PhD in Ruhr University in Bochum with Professor Fischer, and okay, so now it's fine. Okay, so Andreas did his PhD in Ruhr University Bochum, where his thesis title was Linker Functionalization as a Tool for Importing Functionality into Metrologic Frameworks. And after finishing PhD, he was visiting researcher at Hokkaido University, Sapporo, in Japan for a couple of months. No, more than a year.
No, it's twice.
Yeah, twice in two ways. Yeah. Okay, and then he was a researcher in TU Munich for a year, and after that he went to USA. He worked as a postdoctoral researcher at Sandia National Laboratories, where his research was based on the development of new hydrogen storage materials based on metal hydrides and designing negative thermal expansion in framework materials. Currently, he is working as a junior research group leader at TU Munich, TU Dresden, and he is exploring the applications of coordinating frameworks for different energy storage as well as some other applications as well. Besides, he has been recipient of one of the big fellowship in Germany, that is Liebig Fellowship for chemist in chemical industries, and he is working of that fellowship. Beside, he got two fellowships from DFG also. Yeah,
From DFG,
DFG, yeah. So and he has so many awards in his list. So I will not take much time, but yeah, welcome again, and I'm looking forward for your talk.
Thank you, Khalid, for the nice introduction and for the presentation. Yeah, I'm very happy to speak today in front of you. I will tell you a bit about one of our research areas where we look at side chain functionalization of covalent organic frameworks. So we want to sound okay? Can you hear me all?
Yeah.
Okay. Where okay, thank you. Um, where we look at the attachment of side chains to the backbone of these framework materials and try to figure out how this can facilitate delamination. So just to quickly show you where I'm from. So here's Germany. Um, I'm from West Germany. I'm now working in East Germany. And yeah, we are over here. So it's roughly a 9-hour flight. I was first in Chennai before I came up here, so I've been now for 1 week here, and I so far had a really good time. Um, Here about Dresden. So Dresden is here on the east side of Germany at the Elbe River. It's a very nice historical city, so many Baroque buildings. We have this very nice opera house, the Elbe River, and here's the Frauenkirche, which is the largest church in our city. Dresden has roughly 500,000, 550,000 inhabitants. It's the 12th largest city in Germany. Not as big as Rotterdam. So TU Dresden has roughly 30,000 students and 8,700 employees. There are 5 different schools featuring 7 um, faculties focusing on different types of research like engineering, science, and so on. Roughly 60% of the students are actually abroad, and since 2012, this is an excellent university. So that's a certain certain funding from the German government, which is allocated to currently 11 excellent universities across Germany. So they get a bit more funding. And apart from the university, there are several research institutes. So there's 3 Max Planck institutes in Dresden. 9 institutes of the Fraunhofer Society. There's 3 Leibniz institutes and 1 Helmholtz Center. So these are all different types of institutes that work somewhere between university and trying to bridge the gap or trying to do some fundamental research as well. So to my background, as Cardiff already nicely introduced me, I was working for Professor Roland Fischer from 2010 to 2017. At first at Full University Bochum, then at Munich. So that moved in that time. The main topic of my PhD was flexible metal-organic frameworks. So metal-organic frameworks that can change their pore size, certain outer stimuli, for example, heating or gas adsorption. After that, I moved to Sandia National Laboratories, where I worked with Mark Ellendorf and Vitali Stavila. My main topic was working on these magnesium ore hydrides here. These are very interesting materials for hydrogen storage, since they have a very high hydrogen capacity. So magnesium ore hydride has roughly 50% hydrogen content, and so far it's still kind of unusable. You get it out once, but not back in. So this is a big research area. And apart from that, I worked on negative thermal expansion. And since the beginning of 2020, I'm an independent researcher at Dresden. So the system is a bit different than out here. So we don't have this assistant, associate, and full professor levels. We have full professors and nothing else. So I'm doing a habilitation, which gives me the right, after I finish it, after I wrote another thesis, to officially teach, and in the topic that I intended. So I already have a small research group with 2 PhD students and currently 3 undergrad students. And yeah, we are working now on covalent organic frameworks. So the German system is also always wanted that you be distinct from your supervisors and do something new. So yeah, we are looking now since roughly 3 years into making 2-dimensional delaminated covalent organic. So to jump into the topic, there are different types of porous solids. So this is a very nice overview from a review from Andy Cooper, where the properties of different traditional porous solids are compared. So you have the zeolites. I probably don't have to explain their advantages. They are used in industrial scale catalysis or in detergents to get ions out of water. These materials have a very narrow pore size distribution. They are mostly micropoles, but they are all samples. Their crystallinity is very high, and they are very stable. So they are very high thermal and acid base. Metal organic frameworks, a topic that Cardiff is also very familiar with. They have some advantages over the zeolites. They can have ultra high porosity because you putting these linker molecules, these spacers, which means metal sites here, and you still have very crystalline materials, but their stability is lacking because you only have coordination bonds to keep these porous crystalline frameworks together. And the class of materials that I want to talk about today are covalent organic frameworks. So as the name says, you have again a framework material. So from molecular building blocks, you are building up the structure, and these molecular building blocks are linked together by covalent bonds. So these are also either micro or mesoporous. They can have ultra high porosity. The pore size distributions are usually narrow. The crystallinity is somewhat discussable compared to the other materials, and their stability is really depending on the linker chemistry that we use to frameworks now. So I will explain a bit more about the linker chemistries and abilities covalent. Then you have porous organic polymers. Some people say that you call your porous material porous organic polymer if you are unable to crystallize your top. because this is kind of the major difference. So it's often a non-crystalline organic framework. They are mostly amorphous. You have usually micropores, pore systems. Pore size distribution is quite broad, though, but the stability, so here's the difference also to pores, usually have quite strong bonds, so you use like Suzuki couplings or similar very fast reactions that form stable bonds to the couplings. And then last class of materials that's gaining more and more attention recently, also in respect, for example, for liquids, are these porous molecular solids like metal organic polyhedra or organic cage molecules. And there's not so many examples, so there are more and more coming. But when this table was made, there were very few examples on them actually being porous. Now there's more. They have a narrow pore size distribution. Their crystallinity is high, and their stability is somewhat poor because you have basically each pore is confined to one molecule. It can be, which makes them a solution. Yeah. Let's continue with the covalent organic frameworks. Here's already an example of a layered covalent. So these layered covalent organic frameworks belong to a class of materials we call 2D framework materials. So traditional 2D materials are, for example, protein. So I define 2D materials as materials that have less than 10 layers. I think there's a lot of discussion in the literature. Some people call much thicker materials 2D materials, but I think that they should be very thin, 10 layers or less should be the case. I mean, optimum would be 1 layer, but it's very hard to achieve one scale. So conventional materials would be graphene, like phosphorus, different transition metal dicalcogenides like lanthanum sulfide or hexagonal boron nitride. The framework materials that are 2D in contrast would have, apart from these very dense structures, pore systems. So the polymers, the covalent organic frameworks, they kind of look the same, but they have a major, in my opinion, a major difference. For the 2D materials, you have first the crystallization process. So you have, for example, here these tryptophan units, and they align first into a crystal, and then they are polymerized. And then you still have measurable single crystals, for example, of this material. And then you can exfoliate them, and you have your with the cost, it's a bit different. So the crystallization and the polymerization are happening at the same time, which means that the materials are not so crystalline, and the metal organic frameworks, for them it's in a similar fashion. So you have your metal SPU and your organic linker. They are arranging while they are crystallizing, while they are polymerizing the building blocks. If you look at the developments of these classes of materials, is kind of interestingly linked also to the discovery of protein. So the layer structures, they were known, for example, most since the 1990s. Most were known. The first actually discovered POFs or described POFs in the literature, they were also two layered materials. And yeah, roughly after the Nobel Prize in 2009 was awarded to the from Manchester, people also started eliminating these frameworks materials. So, for example, this MOF elimination was actually done by Tadev's postdoc supervisor. So just by solvation and ultrasonication treatment, these sheets can be delaminated. For the costs, was interesting. This study was done by Tadev's PhD supervisor. So this is a delamination, first example of cost delamination, where ball milling was used, and for the 2D polymers, this was also a sortation process. And there are some other examples where, for example, monomers are aligned on a a surface and then polymerize there to get essentially a very thin material polymer on top at the water interface. So I've been talking now a lot about these framework materials. Why do you actually want your material to be so thin? What are the advantages? So in electrocatalysis, for example, if you have a functional unit in your material that contains active metal side, the downsizing can, for example, affect the band gap of the overall framework, and you have better access to the catalytic side. So the catalytic sides are the freestanding framework and not buried somewhere in the middle of your material. You should have a much higher turnover. For gas separation, you imagine a membrane. So this is an example of like a aluminum oxide membrane that has pores, and you cover it with a bulk framework material with a bulk crystals. The diffusion will be much slower. The permeability will be much slower, contrast to having just a very thin layered structure. And you also can imagine that these crystals, they will arrange not in such an ordered fashion in comparison to the sheet materials, and you will form will much more easily form voids and cracks in the structure covering your support than if you have these kind of sheets that you just lay on top, then be glue to it with some things. And for energy storage devices like supercaps, this is expected to have much quicker charging. The interaction sites are better accessible, and in the most ideal case, the charge transfer is dominated by the redox kinetics and not by the diffusion kinetics with the bulk of the material. So, what are actually covalent organic frameworks? So the first example of a covalent organic framework was this one, published by the people of Miyagi in 2005. Essentially, you can imagine, if you remember your organic chemistry, I don't know how many have a chemistry background here, you can primarize this acids by this condensation reaction, and then you get this peroxide anhydride ring. And if you imagine that you have a ditropic boronic acid, same type of reaction for the same type of condensation reaction, you can form a framework with a lot of these peroxide anhydrides, which are bridged by bisphenylene. And this is one example of a top. You form these 15 angstrom large channels, but since this publication, a lot of different bonding chemistries have been established. So for every type of different bonding chemistry, there are certain advantages. Some are very easily accessible. Some give additional properties to the material. Some make help conjugating the structures. But the difficult thing is that you have a lot of different chemistries, so each bond type needs you to understand the chemistry. So this is also from a review from Umayagi. I added just at the end some newer ones that I find very interesting. So porosine and the boronate esters, they were the first ones that were discovered. The triazines were actually discovered by Cardiff's second postdoc supervisor, by Arne Thomas. It's maybe one of the major players, or the major player of the top in Germany. And these imines were first reported in 2009. It was a very simple reaction. It's probably the most used reaction up to now. Then these ketoenamines are quite frequently used because they have a hydrogen bonding between, which locks the material kind of in and makes the material more stable. And phenazines are very interesting because they continue the conjugation inside the material. Schneemann are very interesting because we have these Tito groups here, and they have been used excessively for battery studies, for example. Then yeah, all kinds of bond chemistries that you can imagine to form a molecule in organic chemistry, they can to some degree be transferred off-land. Recently, there's also these imidazoles that we are working on in my lab for the Swinulines, also discovered by Cardiff. We recently found this dithioine bond, which is very interesting for lithium sulfur battery. And yeah, there are more and more reports and more bond systems to be discovered. So I want to talk today about imine-enriched COFs. Because this is what we're working on, and it's a pretty nice chemistry if you get started in the field because it works most of the time. So other bond chemistries are more difficult and you don't get it. So essentially, you are reacting multi-topic aldehyde with an amine, goes through this iminium transition state. You have to feed in some hydrogen, for example, to protons, for example, to acetic acid addition, and then you form this imine bond. It's very important that this is a reversible process, because this helps making the framework structures that you generate very crystal. Because you can essentially repair defects that form during the reaction process. So two examples that were early on reported are these 3D COFs. So we have this tetraphenyl methylene that helps generating such a diamond structure, and these anilines here, they are bridged with this aldehyde forming a 9-fold interpenetrated network. And shortly afterwards, 2D framework was discovered. It's called LZQ1, where you essentially same reaction 2D. You have this trialdehyde here, you react it with phenylene diamine, and you get this very well studied called LZQ1 imine bridge. For getting core environment you want, it's also very important to look at the proper linker design, because the geometry of the linker dictates the topology of the framework. So depending if you want very large pores, very small pores, rectangular pores, hexagonal pores, you have to look at the building blocks that you use. For example, if you have this building block with a C3 rotational axis, linear building block and hexagonal pore systems. We're looking at this heterotopic building block with a C2 geometry, so it's not a C4 rotational axis here. And mix it with this aldehyde, so linear linker, you are ending up with such a square grid topology. Example, and if you are looking at this tetraphenyline ethylene linker, you can end up with such a carbonyl lattice. There's a lot of different possibilities of combining different linkers in your cost. So now I will jump into our research results on the sidechain functionalized COFs. The first question is probably why do we want to use sidechains? So during my PhD, I already worked quite excessively with sidechain modified metal organic frameworks, and as a researcher, you often take something that you already know and combine it with something new. And we found that these, in the case of metal organic frameworks, you have sidechains. In certain types of metal organic frameworks, you can make it flexible, so they can change their pore environment absorption, for example, so changing, and these side chains also include some absorption selectivity for certain gas molecules. And the third thing that we discovered was if you have a layer to the framework, metal organic framework, and you have side chains attached, this makes it very easy to exfoliate the frameworks upon solidification when they are dispersed in solution. You are able for these copper PVC frameworks functionalities get sheets as small as 1 to 2 nano layers upon attachment of these sections. So we did the same with the covalent organic framework. So here we have pyrene-based linker. We combined it with this terephthalate, which is functionalized in 5 position with these kind of organic side chains. So we have a branched side chain, a hexyl chain with a heteroyl group in 2 position. We have this octyl side chain. We have a hexyl side chain, and just for the sake of pairing it, we have a material with no side chain. So we have a series of 4 POPs, imine-based POPs that we looked at. And first of all, we did all the standard characterizations to know that the material is actually what we wanted it to be. So we can see from the IR spectra that we have indeed the side chains installed. Here we have our CH vibrations. Then what we also can see is that we found the imine bridge, and also we can see that none of the starting materials is left. Second, we have the solid state NMR. You can also see the functionalized materials. We have the alkyne the signals for the alkyne side chains. Here we can see the aromatic signals, and in case of the OH functionalized material, we see the hydroxyl. The same, we also looked at the C mass NMR, so solid state NMR, and we can pretty well assign all the signals to the different side chains, and also the aromatic signals can be assigned to the hydrogens, sorry, the carbons located on the pyrene, and the enriching terephthalate aromatic. We looked then next at the refraction patterns. So if you really look into deep into it, you can see that 001 reflection, which is located at higher angles and representing the distance between 2 adjacent sheets. It's not really visible, but it's shifting slightly. And we see that here's the example. There's no side chains attached to this example for octyl chains. So from a combination of these powder patterns that we refined with computational analysis, we figure out that the layers they are slightly more distant from each other if you have the side chains attached. And this is also one reason that we want, one thing that we wanted to achieve. So if the layers are further apart from each other, it will make it more easy for us to exfoliate them and get yes, sure.
E is equal to 3.87.73. Is that spacing matching with that low angle axis?
So the low angle,
sorry, the low angle, whatever degree found, that should be much clearer.
Yeah, what we see here. So what we see here at the low angles, those are the lattice planes that are within the layer. So this is the 110.
3.87 should come to slightly higher side.
Yeah, that's between 20 and 25, and it's really hard to see. So here in this case, we can see it here as well, here as well. Here you can also, yeah.
Either low angle means that they are some ordered structure.
Yeah, so they are stacked. And at the low angle diffraction peaks, they are all for the the A and the the lattice planes that are along the layer, not parallel to the layer. Yes, exactly. So what we see is that we have a slightly larger difference. Then looked at the accessibility of the force by absorption measurements. So we did some nitrogen absorption at 77K, some CO2 absorption at 195K, and we can see that the materials that don't have any side chains take up more gas, which makes a lot of sense because we have more space and less weight in the material. It's normalized to the weight. And we also see from the analysis of the isotherms, the key methods that the surface area is much lower if we attach the side chains. Interestingly, we see here also some features of mesopores. So this is a good sign that we also induce some defects into the pore structure. We have the side chains present. Similar trends are observed for the CO2 absorption of 195K. One thing that was of our interest was the side chains are very hydrophobic, so they are very non-polar. We wanted to look at water absorption and at absorption of hydrophobic molecules. And what we interestingly see is that water is absorbed only very well in the non-functionalized material, where we only have some hydroxy groups, and essentially the materials with the octyl chain and the branch side chain, they don't take up any water, so they are hydrophobic too. And the heptane absorption then looks a bit different. So the hydroxy functionalized material takes up quite a lot of heptane. But the others, they are basically swelling with the heptane. So they take up a decent amount, but with increasing pressure, more and more hexane is taken up, and it's also dissolved. The side chains, they interact very well with the longer elements.
This absorption is because of anything to do with the frequency that you are having, the space that you are having in the framework?
Yes, on the one hand, the space, accessible space in the framework, but also the interaction sites. When we think that the side chains, they repel the water. They cannot interact with water. There cannot be any hydrogen bonding or any polar interactions. But the frameworks that have the side chains, they can interact with the heptanes, for example, because they can rearrange.
So the vacant space inside, which is showed in some cases about 1 to 2 nanometer. So that has nothing to do with the specific absorption properties.
Only for the non-functionalized materials. Here we have side chains that are.
They are doing the job.
They are doing here the job.
So it's more of a chemisorption.
It's 100. It's difficult. Yeah, it's. I would say it's a physics option still.
The typical energy value of
this I cannot really say. I think it's 50, maybe 50 kilojoules per mole, something like that. Those are the typical. So physics option would be 100 to 100. So I think it's much lower because we can also get the.
Like in between.
I would still say it's rather on the physics option side. Yeah. Because the interactions will be mostly van der Waals.
Yeah, but if it depends on the functional group, then it's not van der Waals alone. You have the specific interactions playing, and that's chemical energy. That's not van der Waals. That's not space.
I think it's van der
That's not the
Waals.
volume. Right? Their strength will be weak. Because there are many things which are tuning the extent of interactions with the guests. Okay.
Thank you for the question. Okay, so what we then next did was, we wanted to learn about the surface properties. So we measured some water contact angles. So in the case of the first material, we pressed the palette. This was not so successful for the other three materials. So here, coated some double-sided tape very smoothly, so it's not so easy because your contact angle can depend a lot on the way you prepare the materials. And we have quite smooth surfaces. There's some roughness, so if the surface is rough, you will automatically get a higher contact angle, and it's not avoidable. It's unavoidable to have some roughness in the environment. So, but still, we see the general trend that we have the side chains attached. The materials will repel water quite easily, and they soak up heptanes, hexanes. I don't show the data here quite well. And if we have only the hydroxy groups located here, the water will get soaked. So one potential application that we thought about is the water separation. So we essentially soak these materials with, with different solvents from the lab. They don't take up any water apart from the non-functionalized material. We are comparing the non-functionalized material here with the octane functionalized material. You can see that for the hexane, for the heptane, for the dodecane, we take much more, we absorb much more of the liquid than in case of the non-functionalized. We are right now struggling to figure out why the heptane uptake is so much higher. This is based on three.
It's difficult to understand how heptane is interacting chemically with this O group, the lone pair of the oxygen.
Yeah.
It's completely non-polar.
Yeah, we are thinking that maybe heptane is stabilizing itself better. So I mean, it's not much. Well, not much. It's roughly 100%. But I mean, we also have a quite huge non-polar limit here.
So what is the maximum length in the structure, the diameter in terms of
2.4
nanometer? The largest one.
Yeah.
Absorbs. How to dissolve?
We dry it in the oven. So this is not an absorption.
Suppose if you want to apply this membrane system,
yeah,
then the option is also
permeability and So in our case, we just heated it out again. We just wanted to do something with it, understand the material a bit.
How many cycles?
So we used for these bar diagrams, we always did three measurements to have make sure it's not by accident the values that we get. So that's why we are also so puzzled why this one is so high. We're trying to understand it. There's some self-propagating nature of the heptane because it's not so different from hexane, right? So yeah. But yeah, we didn't cycle it very often. Okay, so we still want to exfoliate our materials. So what we can see here is from scanning electron microscopy images. So here's the non-functionalized materials. Here are the three materials with the side chains. And what you can essentially see here that the functionalized materials, they have more round edges. They are not as crystalline. And the non-functionalized material has very sharp edges. A bit more crystalline. So for the exfoliation, we did some first screening. So we dispersed our material inside different solvents. So we have here, as an example, the optimal functionalized material, the hydroxy functionalized material. We sonicated them for roughly 1 hour in these different solvents, and then let them settle overnight, and then took a look at the resulting solution. And one very nice finding was that if we have the side chains on there, most of the solutions are quite stable. So, of course, you see some precipitation, but you see after 24 hours nice tindle scattering, and the materials, they are orange in color, and you see that they stay in solution very long. If you don't have the side chains, much more precipitate, and in some cases there's barely any color left in the solution, which means they are not so easily dispersed. And from this, we decided to use the ethyl acetate and the methanol as the solvents to carry out our exfoliation studies. Because certain factors from the AFMs that we took materials pointed us in the direction that these are the most efficient solvents for the exfoliation. So here we have some methanol solutions, and you can see when we make the solution, we have a tindle scattering in the OH functionalized material. After 24 hours, we don't see much. We see that not much is in the solution. We have the functionalized materials. We can see the tindle effect is quite strong even after long times of settling. So this is our exfoliation strategy. So we soak the materials in the solvent. So we have the solvent contamination. We hope that the side chains help in catching the layers. Then we sonicate them, and then have the curved nanosheets inside the solution. So here we can see the ethyl acetate exfoliated materials. So we can see for the non-functionalized material that the flakes that are resulting are very large and very thick. If we have the longer side chains, we can see that the sheets are a bit smaller in size, but also you can you see the contrast is much lower, so they are most likely much thinner. This is the first observation that this approach really works. And then we moved on further and did some AFM studies. So this took us probably the longest time of the study to get these nice AFMs, because we are not from the field really. We need to figure out how do you make dispersion, how do you place them on the right substrate. So we just screened a lot of substrates. And then the next problem is the drying process. Drop your dispersion on the surface, don't dry it big enough, the sheets will agglomerate again, and you think nothing happened. You have 100 nanometers high features, and this took us, nearly 6 months, I would say, to get the perfect conditions to see the size of the nanosheets that we made. So very interestingly, so we did some statistical analysis of roughly 10 to 20 sheets. And we have here this interquartile range, so 50% of the sheets, they lay in this size regime. And what we can see is that if we have the hydroxyl groups, the sheets are much thicker in case of ethyl acetate and methanol. And if we have the octyl side chains, we can get very, very thin sheets. If we exfoliate them from methanol, they are at roughly 1.5 nanometers, which corresponds to 45 layers. One thing that also happens when we do the sonication treatment, we don't only make the sheets thinner, but we also break them along the layers, which is an unavoidable problem, I think, because we need to put in the energy, and the sheets will break along the layers. And so, as a very small proof of concept that there's some benefit to having these sheets is we integrated them into separator membranes, which we put into the lithium-ion battery type setup. So we have a PDF solution in DMF, and then we added some of this octyl functionalized material. Then we drop cast the ink that we made with PDF and the copy onto a substrate, and by the doctor blading method, we generate this nice film, and then we cut out this kind of membranes that we could put lithium ion battery. We used a very simple setup, so we have here the top in the PDF separator. We use lithium foil and lithium iron phosphate as the cathode material, and yeah, we use a carbonate-based electrolyte. So the LiPF 6. So what we can see actually, if we integrate this COX into this PDF membrane, we can see from the impedance spectroscopy that the diffusion of the of the lithium ions to the COX PDF membrane is much quicker. So we see the resistance, which is proportional to the diffusion. And if we don't have the pump inside, the diffusion coefficient is much higher. Of course, if you look at commercial lithium-ion batteries, we use completely different separators, cell guard based on PP with much larger bores, and those our values are not really comparable. But we just wanted to see the benefits of exfoliating. And we see also, yeah, the overpotential is much lower as we don't have any costs inside the membrane. We could run this battery for roughly 500 cycles. It was stable. This is a small proof of concept, but we are not challenging current battery. So to conclude my results, the side chains alter the surface properties, so get a nice sorption selectivity towards oils and other hydrophobic molecules. We can exfoliate the materials much easier, so the side chains help in the exfoliation process, as we saw from the AFMs. We form quite stable solutions, so we can integrate them easily into membranes. And as a proof of concept, use them as a separator membrane for this ion batteries. That works. So, what is our next steps in this research? So, we want to deposit our sidechain functionalized POFs onto porous aluminum ceramics. We are doing that, and we want to compare those two mixed matrix membranes where we integrate our POFs. Currently, I plan to use this for research of K-number upgrading as a potential application. And yeah, we can adjust the side chains that we have on there. So if necessary, we do some more organic synthesis, see if we can use the performance of these membranes that we have made. Then I was pretty intrigued by the stability of the side chains in solution. So we see this for 24 hours they are stable, and I was interested in how are these nanosheets assembled in the solution, what is their state. So we did some synchrotron measurements on these for some small angle X-ray scattering experiments at the synchrotron at the diamond light source. It's close to Oxford in the UK. And from these you can learn something about the shape and the size of particles in solution and about their ordering. So these are our first results, and the very interesting thing is that we see so it's very difficult for me to understand small angle X-ray scattering. We do this together with some experts. The take-home message that I got is that we see a peak in the wide angle region here of the sex measurement, and this corresponds to distance within 1 pore. So somehow the optical side chains, they are stabilizing the solution so that you still have a crystalline features in solution. So we are right now looking into the origin of that and trying to understand. And yeah, so I want to acknowledge my PhD students. So most of the work that I showed today was done in Kita, now as a PhD. And then I want to acknowledge yeah, all the helping hands, so from the inorganic chemistry department, from the bioanalytical chemistry, who did all the mass NMR measurements, from the Leibniz Institute for Polymer Research, it helped us with the contact angle measurements, and the Institute of Applied Physics, they gave us access to their AFM, which we use for the determination of the average sizes. Then, yeah, thank you for your attention. So here are some photos from a recent conference. So that's how I know Cardiff, but I know now maybe since 10 years roughly. And he was also on the organizing committee of a meeting that we had in Dresden. Here we together all the organizing committee members and speakers. This is Umayagi. So he's one of the innovators of our field. And we had a really nice
Same shirt.
oh yeah. Yeah, I want to thank Cardiff for the invitation and for your attention, and if you have any questions, please don't ask. Thank you.
What is that structure?
Yeah.
Kind of umbrella.
Yeah, so during
Because
our
I'm asking because this color is matching with that your membrane color.
yeah, that's true. That's true.
This is one case actually. The one what he showed in at the start. So that lady was there who was building this out of this.
So we had one guest, so for some evening entertainment for scientists. So she's a mathematician slash artist, and we built larger structures out of bamboo and this linen.
I'm still intrigued by the absorption plot that you showed by your assistant. Can you please go back to that?
Yeah, sure.
Where you have ethanol, hexane, and many others. Yeah. Interesting thing is that the first entry and the last entry, hexane and ethanol, they are having similar amount of the while you have only one carbon extra, CH2 extra in heptane, and its absorption is so high, right?
Yeah.
1400. This is one thing. And the second thing, which my chemistry knowledge is that the internal diameter is not playing any role whatsoever in these things, in absorption, variation, species variation of the absorption. So I so far I had thought that the cups are working where you can engineer the internal diameter, and those diameters are actually key to the specific absorption qualities of these systems. It looks like no, it is the functional groups, as you are saying.
Yeah, I mean that's
So now you tell me in these kind of agglomerations or spatial structures, what is key in giving such an uniqueness of gas-specific absorption?
So yeah, this is also something that we are still trying to figure out. I mean, one thing you have to consider, you have the sheets that can also move and swell, right? So it's a
That is your breathing mode.
Yeah.
And at room temperature, what should be the breathing mode?
More solvent is adding,
They are actually expanding.
Yeah.
Expanding.
Yeah, the layer.
Or the layers.
The layers. So distance of the layers.
So you are saying that under the layer, this gas may be trapped, something like that.
Yes.
No.
This is the solvent.
These are all solvents?
So,
No.
Yeah. So
So I think core is
Yeah.
also working somewhat. Core, because they are high surface area material.
If you have to consider the
What is the role of the pore? That's my question. My
Cores
question
are
is,
also work.
what is the role?
They are keeping the solvents and they are using
How? Because the size is so large.
size is not-
Yeah, 2 nanometer or 1 nanometer. And these solvents are typically few angstrom
But
diameter.
some warm solvent. You consider not only one molecule. It will be more because 1400 times 1400%.
Difficult to understand that.
What's the origin of selection?
It will be when hydrophobic group is there, they are repelling water. When hydrophilic
So it
group
can
is
selectively absorb any gas.
no, not there. No, the hydrophobic is non-polar.
There is
They will
something
be
which
there.
you are missing in the interactions. It cannot be simply that. Because you see, heptane is purely hydrophobic. And it is now responding to your OET. And OET is not hydrophobic. The interaction is
That is the
possibly
thing.
largely
Can
via the
you go
oxygen
back?
pairs.
Yeah, that is the some kind of anomaly I can see. The hexane is purely non-polar.
So there must
And
be a
the
lock and key
alcohol
mechanism.
is quite polar.
There is
Okay,
some
so they are equally absorbed.
there is some lock and key mechanism in three dimension of that structure. Maybe those things which are protruding outside, when you stack them in three dimensions, those there will be some voids created, and maybe they are playing some role.
it's also, I mean, here's the question is also, it's not an adsorption. So here we have adsorption, so surface interactions. Here, this is most likely absorption, so volume interactions.
These are not actually monolayer.
Yeah.
So
Definitely,
if you go back
that's
the
right.
surface area,
the bulk materials, and actually when
Yeah.
we talk
But
about
not
gas,
this. The surface area. Just that.
This or the other.
Yeah, this one. You can see this is not a monolayer system. It is just absorbing as much as it
Not that, but those are the observations. So I'm trying to understand in molecular terms what gives its chemical sensing, and it's very specific because it can identify, you can design, you can engineer materials to specifically absorb particular gas and not the others. So that thing is there.
Yeah, I mean, this
Yeah.
is not necessarily novel.
Yeah, so you can back engineer. If you understand the nature of the interaction, then you can back engineer things. Then that can be used for gas separation.
Yes, I mean, these
Right?
things.
That is the main goal of these things.
Yeah. So this is what we want to do. We want to build membranes in the long run.
Right. So thank you.
With sacks, small angle.
Yeah.
So that 24 angstrom. So what? Because normally it works as like if you have like particles of a similar size, they arrange in a fashion and you get some signal in sacks.
Yeah.
But in your case, all these particles would be of different sizes. No? So
Yeah.
can you speak what you
Thing is, this feature here that you see very often this pore. And yeah, I mean, this is how it works for like mesoporous carbons, for example, right? That you have a pore size repeating, and you see the diffraction at that distance, right? So I imagine it also that those guys, they are swimming in solution, and if you have these side chains, they are probably stabilized better, maybe through interactions with each other, and then yeah, they give this scattering.
I have one question. Like, you have a hydroxy, you have hexa, we have like branch one and block. Couldn't you synthesize it with oxy? Yeah,
That's a good
way,
question.
that would have been much more like easy to analyze.
So we were actually looking into the metoxy as well, but we wanted to have something that didn't have any side chains. And the OH is just the easiest to, it's stabilizing itself with a high, no. We have a hydrogen bond here, it's very nice and stable. So, but yeah, the metoxy would have been a good idea. We made this, but we didn't study it.
And the second question, can you go to the image where you showed the different solvents and having the dispersion, different dispersion in acetone and all those. Okay, this one. So if I see it there from entire acetone and acetone,
I see some color,
Yeah.
and which is not the color of the bottom one for the hydroxy one. The bottom one, yeah.
Yeah.
So which is not there in anywhere around.
Mm.
So what is that color?
I think it could be remaining of the
Yeah.
taurine
Yeah,
link.
because if you look into that, acetone and ether are very good solvents.
Yeah.
Maybe taking out some of the unreactive molecules.
It could be. I mean, we made this when we were very early in the study and didn't know how to activate it and so on, adding materials. So yeah, I mean, this dark orange is the color of the.
And this is what we observed. Like, other colors could be because of the pop, because sheets you showed have the same color. And in this case, this color is typically from the something which is reaching out or something like that.
Yeah, and I mean, those guys, they are not solving very well. You see nearly everywhere. It's after one night, it's all precipitated, and then probably the organic molecules they stay. Sorry? Yeah.
Why it moves from base activity? This like capacity wise.
Sorry, question is not clear.
This is yeah.
The one?
Yeah. No, this is okay. The slide is fine. Go to yeah, that's fine. Yeah.
When R equal to OH,
Yeah.
then why ethanol so lower activity? Because OH is a hydrophilic.
Mhm.
OH ethanol is also hydrophilic. So it should go better activity.
Yeah. I think this is it's very difficult to say. This is just a gravimetric test where can make a lot of mistakes actually. So so you are dropping the solvent until nothing is absorbed anymore. And I think one reason why you have more uptake of the solvents in the functionalized materials is because you also have more defects. So you have larger pores. So it's on the one hand the interactions, and on the other hand the defects. You can see that actually pretty nicely. Here the optical functionalized material has this huge hysteresis here, which is a good sign of disordered macropores. So they probably also help. So you're not absorbing on the surface here in these experiments. You are having droplets essentially inside the pore space, and it's not so defined as we would like it to be.
Any more questions? If not, then let's thanks Schneemann again